So we all know, and you hear about it regularly, that the CO2 level is therefore rising, and that this could have very significant implications for the climate patterns of the planet, the so-called global warming or global climate change, which is a great concern to us at the moment. And the question is, how long can we afford to keep burning fossil fuel and pumping CO2 into the atmosphere without there being some dramatic change in the climate of the globe? So this is a worrying factor. The other, of course, is that the availability of fossil fuels is getting harder and harder. So it was easy to find oil and gas and coal over the last 100 years, but it's getting more and more difficult. So there probably is quite a lot of it still on the planet, but it's actually being able to retrieve it and use it. So we've got two factors here: availability of fossil fuels and also the problem of CO2 emission into the atmosphere. So this raises the question, what's the alternative? Is there a way in which we can develop new technology which will be independent of burning fossil fuels or photosynthetic products which were synthesized a million years ago? And so this brings into play the idea of developing the same catalytic reactions that the leaf carries out. So what are these two catalytic reactions? The first one is splitting water using light energy. Can we develop a catalyst that mimics the photosynthetic process by absorbing light and carrying out the chemistry to convert water into oxygen and hydrogen? This is the challenge of the so-called artificial leaf or artificial photosynthesis. And if we can do that, then we already have a fuel, because we produce hydrogen, and hydrogen is a fuel, so we can burn the hydrogen by recombining it with oxygen back to water. So we have a cycle which goes from, maybe I can draw a figure now, it might be a good idea. So this is the cycle. So we have H2O, and we're going to sunlight to split it into oxygen and hydrogen. Now for this stoichiometry, we have to put a 2 there, actually, and a 2 there. Okay. This is driven by sunshine to drive this reaction, which requires energy. But you've now converted the sunlight, the solar energy, let's call it solar energy, we've now converted the solar energy into the energy of the chemical bonds of hydrogen. And now if we now burn this hydrogen with oxygen back to water, we do that, we get out of here energy. And so this energy will drive technology. And in fact, this is what we do anyway. This is what photosynthesis does, except this hydrogen in photosynthesis, it's usually converted by combining with CO2 to, I'm going to write biomass, which are carbohydrates, all the molecules that make up living organisms. That's what happens in photosynthesis. But in artificial photosynthesis, you either would take the hydrogen or you would, again, combine it with carbon dioxide, and you make some simple molecule, which is an energy-rich molecule. For example, you could make methane, CH4, or you could make methanol, CH3OH. These are fuels, simple fuels. And so you're basically doing what photosynthesis would do, but you're making a very simple fuel. You're using this as a high-energy carbon compound, and now this is a fuel. And this also is a fuel. So it depends whether you want to use hydrogen directly. But to do those reactions, you have to have a catalyst. You have to have a catalyst here, and you have to have a catalyst here. That is
an agent that will help the reaction occur. But clearly, what is very important is that you have sunlight. Without sunlight, this is the energy source. You can't use fossil fuel for the energy. You've got to use something which is available to us on an enormous scale. And the amount of energy we get from the sun is equivalent to 100,000 terawatts. It's enormous. This is the rate at which energy is being supplied to planet Earth. And the amount of energy we're using, 15 terawatts at the moment. Well, this is a billion. You could call this a trillion. This is also equivalent to a trillion. In the form of sunlight. So there is nothing else. There is no other light source. There is no other source of energy which matches this colossal amount of energy available. Tides or wind or whatever, they're all very small. So the energy source really we're forced to use is just as plants do, sunlight. And of course this is natural photosynthesis here, right? So of course in photosynthesis there is a catalyst that carries this out, and this is the catalyst we call photosystem 2, and that is the catalyst which we obtain the X-ray structure of. So we could see the catalytic center, and the catalytic center in photosynthesis contains manganese ions. And again, we know a lot about the catalysts involved in the conversion of carbon dioxide into biomass. We know a lot about that in molecular terms. So with this information, as I've said before, this gives us the confidence to develop the artificial catalysts to do the same reaction. And indeed, very recently, colleagues of mine in MIT in the United States have developed a catalyst which is very similar to the catalyst that we have in the leaf, so which will carry out this water splitting process. So the challenge then is to develop robust, cheap catalysts that can carry out the photochemical reaction of water splitting into oxygen and hydrogen, and to develop further catalysts, again made of cheap, abundant materials, to convert hydrogen into a high energy organic, simple organic molecule like methane or methanol. And that can be then used as a fuel in the chemical industry or to drive, or in the normal way that we would use oil and gas.